So calculating the moment of inertia and parallel axis theorem. We're going to talk about this parallel axis theorem later, and it's going to help you figure out the moment of inertia just about anywhere as long as you know the moment of inertia of the center of mass. Okay, things rotate nice and smoothly when it's rotated about the center of mass. Then it has least resistance that way. However, if it's rotated off the center of axis, off axis somewhere, then it starts to get really like wobbly and it's very unstable. Okay, so here, let's say we have 4 particles of mass m are connected by massless rods to form a rectangle of sides 2a and 2b. Okay, so from here to here is 2a. Sorry. Thank you. Can you guys see?
Yeah.
Thanks, Aditi. All right. So the separation horizontally for each mass is 2a, and vertically it's just 2b. Since it's rotating about the center of mass of the system, so this is the axis of rotation, right? So it's turning about this axis right here, where the center of mass is already located, right? So this is the actual pivot point. Okay, so this is the pivot point right here between these two, and pivot point is right here for these two. Okay, so the distance from the pivot point to where the mass is located is actually r, right? So this r from here to here is equal to a, basically. And similarly, here to here is also a, and here to here is a, and here to here is a. I'm not going to write those in, okay? So if you were to think about the center of mass, how this thing is going through the center of mass of the whole system, okay? We say I sub Cm, okay, is equal to sum of, right, mr squared. There are 4 masses, right? There are 4 masses times each of the r's happens to be a, right? Okay. So the moment of inertia for center of mass of the system happens to be 4 times ma squared. Okay. So rotating about its center of mass is the least resistance. Okay, it is least resistance. So I sub Cm, right, will always be the smallest possible for the center of mass. Okay, so that's very important. And okay, because it's a natural point of rotation, it's going to have the least resistance of rotating. Okay. However, let's say we were to rotate it about here instead. Okay. So for this one, it was rotated right at the center of mass. So everything was nicely balanced. But here now is going to be here, where it's not the center of mass. It's going to be wobbling around, right? Well, let's see if this one's going to be more resistance than this. Okay? So now let's take a look at I nu. Right? So this is a new moment of inertia is equal to sum of all the mr squareds because they're all particles. Okay? And because this is off axis, right? Off the center of mass axis. Therefore, right, we have, let's call this M1, M2, M3, M4, okay? Just so we can identify them. So M1 has R1, which is 0, right? Plus M2, R2, plus M3, R3 squared, plus M4, R4 squared. Now, M1 has radius of 0 squared, plus M2 has mass m, and it is 2a quantity squared, plus M3, which is m, times the radius of 0 squared, plus M4, which is m, times the radius is 2a squared. So my new moment of inertia is equal to, well, m times 0 is 0, here, plus m times 2a squared is equal to 4a squared, plus 0, plus m times, here again, the quantity 2a squared is equal to 4a squared. So my new moment of inertia, when we rotate it off axis through one set of mass here, right, this becomes 8 ma squared. So this definitely has a lot more resistance rotating than that. Matter of fact, it's twice as much more resistant. Okay, so this is the radius here. Instead of radius being from here to here, this is radius from here to here. So here's the radius, R4. Right? This is R4, and this is R2. Right? Okay, which is equal to 2a, and this is also equal to 2a. All right. So notice when it's not rotating about the center of mass, it's a lot more resistant. Okay. So now, once we understand that, let's talk about how we can utilize this idea to figure out the parallel axis theorem. Now, parallel axis theorem helps you calculate what the moment of inertia is going to be when it is rotated away from the center of mass's axis. Okay? So, parallel axis theorem states that the moment of inertia parallel, right, axis parallel to the center of mass, is equal to the center of mass's moment of inertia plus mh squared. And let's talk about what this we know what this is, but mh squared, we don't know what that means. Well, I defined it all here. So I parallel means moment of inertia about a parallel axis to the center of mass. I sub Cm is equal to moment of inertia about the center of mass axis. H is parallel axis distance away from the center of mass axis. Okay? And this capital M is total mass of the body. So what does that mean? When we were working on this, right, I sub Cm was basically 4ma squared from the previous page, right? So because this is A, this is A, this is A, and this is A, right? So ma squared plus ma squared plus ma squared plus ma squared, 4ma squared. Now we're going to use this. We already know what this was because we did it previously, but I'm going to use this and prove it with using parallel axis theorem to see if we could get 8ma squared using parallel axis theorem now. Okay? So here we go. Ready? So this is already done. This, what's my H? Well, my center of mass axis should be this, right? This is the center of mass axis, right? I sub Cm, which we already know as 4ma squared, okay? But this is the parallel axis. So this axis right here is parallel with my center of mass. So this is my I parallel. The distance from the parallel axis to the distance where the center of mass axis is my H. So this is my H value right here. Let's use a different color. So this here is my H, which happens to be A. Okay, you can see that this is only half as much as this total distance here, which is 2A. Okay, so H is same as A. So according to our center of mass, right, and mh squared, let's use that parallel axis theorem to figure out what my moment of inertia is. So here we have I sub Cm plus mh squared. Well, we already know what I sub Cm is. We already calculated that and we proved it to be 4ma squared. Okay. Plus, our total mass is 4m. Right? We know that, so that's easy. But h is a, so we have a squared. So, therefore, my parallel axis moment of inertia becomes 4ma squared plus 4ma squared. I get 8ma squared. Okay? So we get exactly the same as finding the moment of inertia without using the parallel axis theorem. Now, obviously, it's a lot easier if you were to use without the parallel axis theorem on this, but when we have more general shapes and different, it's a lot easier using the parallel axis theorem than the other way. You'll appreciate it a lot more when the system gets more complex than the symmetrical objects. All right, and then what I'm saying is, look at this. Like if we had something like this, like more general shape, right? Then it becomes uh, pretty, serious, right? It's kind of hard to do. Therefore, um, you have to really use parallel axis theorem in this case. So we're going to try to prove, right, how this parallel axis theorem comes about. You don't always have to prove it to use it, but we're going to at least prove it once so you can actually see what that means. So if this is the actual center of mass for um, axis, right? So this is, let's say, I sub Cm, okay? And this here is the axis that is parallel with my center of mass, which is parallel axis, okay? And this is tangential, well, this is like, let's say, tangential velocity of the center of mass rotated about this parallel axis, okay? So if the center of mass of this whole object happens to be located right here, let's say, right here, then the rotational, right, action of the center of mass and the velocity will be tangential of that, okay? So this will be V tangential, right, for the center of mass, okay? So when this is rotating, right, we have omega, right? So this omega and this omega, they're all same because they're all rotating at the same rate, right? So same omega for, right, I parallel and I sub Cm, okay? So whether you rotate it about here or rotate it about center, the same omegas, okay? So make sure you understand this is the pivot point right now, okay? So since they're moving, whether they're turning or moving translational, it doesn't matter. Once it has motion, it has kinetic energy, right? Because this is in motion. When it's in motion, it has kinetic energy. It has translational kinetic energy, which is the center of mass is moving, but it also has rotational kinetic energy of the whole system because it's rotating, right? So um, translational of center of mass is V tangential, right? This has V tangential part. This relative to center of mass is rotational, right? And that's omega. So based on rigid body approximation, the system rotates through the same angle delta theta as measured by observer fixed at any parallel axis. Therefore, you can use I sub Cm for the moment of inertia for K, E relative to center of mass, right? Then it becomes this. So translational kinetic energy becomes 1/2 total mass times V sub Cm squared, plus this is rotational kinetic energy, which is 1/2 I sub Cm omega squared. Okay? So if we substitute V sub Cm here with omega r, but r happens to be h, okay? The rotation of my center of mass about this parallel axis, the radius of this center of mass is r, and that r is same distance as h, okay? So R is same as H, right? Because we know that V is equal to omega R, but V sub Cm is equal to omega H in this case. So if we substitute this into here, we get that. Okay. Then 1/2 I sub Cm omega squared just remains as it is. Okay. So if we factor out the omega square, right? Factor out the omega square. So I'm going to factor out the 1/2 on this side. So 1/2 on this side. And factor out the omega squared on the other side. Okay. So what we have is mh squared plus I sub Cm. So this becomes the total moment of inertia which is the parallel axis theorem. And that's how we get that. All right. So now that we proved it, we can always use it. Right? All right. So let's take a look at continuous mass distributions. So let's say we have, like, like this looks like a pretty thick rod here, but let's say we have like tiny, like masses all next to each other, right? So you have mass here, mass here, mass here, mass here, like that, right? Just continuously distributed out, okay? And then we just happen to have mass here, right? Just one part of these, all these masses, okay? So this one little section of all this masses is my dm. Right? And from the location where this mass is located from the center of, from the axis, this is my r. Okay. So we will call this our origin, 0, 0, right? So this is 0, 0, 0, right here. Right? Therefore, if we were to use calculus to solve for moment of inertia, okay, we can say, since this is uniform density, right, I guess we could say lambda, which is the uniform density of linear density, is equal to mass divided by length, right? That means the total mass divided by the total length should be exactly the same proportion as this little tiny dm, right, over that little tiny dx. They should be the same proportion because these uniform density. Okay. So if we solve for dm, my dm is really nothing more than m over L dx. Okay? So this is the crucial part right here. So whether you are doing with linear, so this is linear density, right? If you have area, and area density is sigma, right? That's mass over area. And then volume will be rho, right? So let's write that down if you want to. So you could say like L sigma is rho is basically mass divided by volume. Right? Sigma is equal to mass divided by area, and lambda is equal to mass divided by length. Okay, so depending on what's given to you, you have to use whatever. Therefore, I is equal to integral of r squared dm from, right? So here, this dm, it's going to be replaced with m over L dx. Okay, so that is equal to, right? R happens to be my x. So R is equal to x. Dx is that little tiny bit, right? So I'm going to replace the R with x squared. And then I'm going to replace my dm with m over L, right, dx. Well, I will integrate this from 0 all the way out to L, okay, because 0 to L is how far the length of the stick is. So 0 to L. So we know that this right here is constant. So we can factor that out. So now we have 0 to L, right, m over L x squared dx. Now it's easy, right? So m over L, right? If we integrate this, we know it's going to be x cubed over 3. Evaluate that from 0 to L, right? So m over L, right, times L cubed over 3 minus 0 over 3. Therefore, one of the L's at the bottom and L cubed will cancel out, giving me 1/3 m L squared. Okay? So, if you are to rotate a rod, thin rod, at the end, so if you attach this to some kind of a ball bearing and spin this thing around, it would have moment of inertia of 1/3 ml squared. Okay? All right. And if you were to look at the last page, that's exactly what we have right here. We have a rod that's rotated at the end of that rod, my moment of inertia happens to be 1/3 ml squared. Now look what happens when I rotate it right at the center. It should be a lot less resistant because this is actually the center of mass, right? This is the actual center of mass. Therefore, it should have a lot less resistance than if it were to be off. So this is 1/12 ml squared. You should be able to derive this, knowing this, and using parallel axis theorem, you should be able to derive that without even using calculus, okay, if you know this. All right, let's do one more. Then I'll let you guys go off and do some homework problems in your group session. All right, so derivation again, moment of inertia about the center of mass axis of a solid cylinder. The solid cylinder is a disk, right, with like, this much thickness. So this is the radius, right? And then this is going through the center of mass axis, and it is, thick. Okay. Well, if I were to look at the surface of this, right? If I were to look at the surface of this, we should be able to figure out, what the dm is, right? We're going to assume that this is a uniform density. That's very important. Okay. So, for those of you who don't know calculus, I'm sorry, but you have to stick with me on this, and you just have to trust me. And for those of you who already know calculus, this should be a piece of cake. All right. We have to look at the surface. This face right here is this. So we're looking at it from here. Right? Here's my eyeball looking at it right here, right? So if we were to take a look at the surface area and we cut out that little tiny dm on the surface, right? So this here is my dm. And of course, this is infinitesimally small, but I blew it up so you guys could see it better, right? So this is my dm that I sliver cut out of my dm. Right? And this dm is this much away from my rotational axis. That's my R. And this dm is cut out this much of my arc length, ds. And I'm cutting out only the thickness, infinitesimally small thickness along my radius, which is my dr. Okay? So this dm, right, sits in my dA, right? This area right here. So my dm sits in my dA. So this is the area where my dm is located, right? The dA, however, is equal to this ds times the height dr. So if this thing was not as wide, and it's like really like, closed up, right? If it's not as infinitesimally like, if it's not like this wide, but if it's like really closed up, you're looking at this as like very small, like square, I guess, right? So it's like if it's like this, like really small, my ds is so small that it's almost flat, right? Then it's just basically this ds times dr will be my dA, right? This will be my area dA, right? Okay. So my dA is just these two multiplied, okay? So it's basically ds times dr, okay? But what's my ds? We already know what my ds is, right? Because from, I guess, back in like rotational or even circular motion, we said theta is equal to arc length divided by radius. Therefore, d theta is equal to ds over r. Now remember, r is constant, right? So my ds is equal to r d theta. So we're going to substitute that into my ds here. So my dA now becomes, right, r d theta dr. This is very important, right? So yeah, you should just memorize this, okay? Therefore, therefore, since this is a area, right? My sigma is equal to total mass of this, right? Divided by area. We're looking at just that one sliver of this solid cylinder now, okay? Just the face. And the rest of it's all going to have to do with symmetry, so you don't have to worry about it. So the total mass over the area basically is equal to total mass divided by pi r squared, right? We'll consider this r as the total area, no, well, total radius, right? So pi r squared, which is same proportion if I were to look at dm over dA, right? So this little tiny dm over this area, dA, should be exactly same proportionality because of uniform density. Therefore, if I calculate for my dm, substituting this dA in here, I have m over 2, not 2, I'm sorry, not 2 pi r squared must equal to dm over, right, r d theta dr. Okay? Therefore, if I were to solve for dm, my dm becomes, right, m over pi r squared. Now this is constant times r d theta dr. Now we're going to use our integral of I is equal to integral of r squared dm. So we start from here. Right? Now we're going to substitute this into my dm. Okay? So need to replace, right, dm. So this will be replaced here. So now I can say my I is equal to integral of r squared times, right, m over pi r squared times r d theta dr. So if I look at this, r here and r here, and this is constant, so here my I now becomes, I have two double integral here. So m over pi r squared can be factored out because it's constant. And I have integral from 0 to r, which is r cubed dr, and integral plus integral of what? Times integral of 0 to 2 pi, right? 0 to 2 pi, I'm making a complete circle, of just d theta. Whew. Now we can evaluate this. Now it's easy. So my moment of inertia becomes, right, total mass divided by pi r squared. If I integrate this, this becomes r to the fourth over 4, evaluated from 0 to r, times, well, d theta, if I integrate that, I just get theta, 1 over 1, right? From 0 to 2 pi. So this becomes m over pi r squared, and that would be r to the fifth, right? I'm sorry, to the fourth, sorry, r to the fourth, right, over 4 minus 0 times 2 pi minus 0. Therefore, this becomes mr to the fourth over 4 pi r squared times 2 pi. Now we're done. So notice how the pi's will cancel out nicely. R squared will cancel out with r to the fourth at the top, leaving you r squared. So now 2 over 4 is 1/2. So we have 1/2 times mr squared as my moment of inertia. And that is that right there. Okay. for the last page, you don't have to memorize all of these moment of inertias. I'll leave this up here for a while. Right? However, I do recommend that you memorize this, right? This is hoop or just particle, right? Or cylinder, where this is solid cylinder. Memorize these two and these two. So 6 total. Just memorize 6 total. It'd be a good idea to memorize just 6 of these. Okay? And that concludes chapter 11. All right? Let's take a 5-minute break.